In this video, we're going to look at what happens when we compose a permutation with a transposition. We're going to start with this particular permutation inside S12 simply because it's big enough to be interesting. We're going to let our transposition be gamma, and that will be 4 goes to 8. We don't need the 2-row notation. It's more compact to write that in cycle notation. It's also important to realize that gamma fixes everything except for 4 and 8. In other words, gamma of 1 is equal to 1, gamma of 2 is equal to 2, and so on. Well, now, our first big question for this video is, can we get the 2-row notation for first do alpha, then do gamma from the 2-row notation for alpha? Now, we conveniently have another copy of alpha down here. Symbolically, the composition would be written that way. In other words, what we are looking at is first do alpha, then do gamma. Now, obviously, this second row is not right because this permutation here is not the same as alpha. So the question becomes, what changes on that second row? Well, that's not that difficult. We just are going to be doing our basic standard tracing algorithm. We're going to start with 1 goes to 7 under alpha, and gamma fixes 7, so in the composition, 1 will go to 7. Now, it turns out that if we look at all of these numbers, 7, 10, 1, and 12 are all fixed by gamma, so 1, 2, 3, and 4 go to 7, 10, 1, and 2 under the composition as well as alpha. When we wind up getting to 5, alpha sends 5 to 4, and gamma sends 4 to 8. So in the composition, we have something slightly different. We're going to have 5 goes to 8. Now, once we get past that, 6 is going to 5, and 7 is going to 3, and 8 is going to 6, and 5, 3, and 6 are fixed by gamma again. So under the composition, 6, 7, and 8 go to 5, 3, and 6. And again, we notice that that is a nice pattern. Now, it turns out that when we get to 9, 9 goes to 8, and under the transposition, 8 goes back to 4. And so what does that mean? Well, it means that when we look at the composition, we're going to have 9 goes to 4. Now, 10 goes to 9, and 9 is fixed by gamma. 11 goes to 2, and 2 is fixed by gamma. And 12 goes to 11, and 11 is fixed by gamma. So it turns out that this part of the permutation winds up just being exactly the same again. Now, when we actually look at what's going on, these two 2-row notations, these two 2-row permutations, are actually very close to each other. The only place where they are different is in these 2 places. In other words, the only thing that we have to do to go from the 2-row notation for alpha to the 2-row notation for alpha followed by gamma is to change the position of the 4 and the 8 in alpha to a 4 over there and an 8 over here in alpha followed by gamma. The places of 4 and 8 just get switched. Okay, now what we want to do is we want to look at the inversion numbers of alpha and alpha followed by gamma to see what pre-multiplying by a transposition does to the inversion number of a permutation. So the first thing that I want you to do is I want you to stop the video and find the inversions of alpha and then count them up so that you can find the inversion number of alpha. So stop the video and do that. So here are the inversions of alpha that I found, and I want to just quickly explain one way of finding them. I basically started with this 7, and then I just went through the whole list of numbers on the second row and asked whether or not they were an inversion. So 710 is not, but 71 is, and so I wrote down 71. 712 is not, but 74 is, and I wrote down 74. 7.5 is an inversion, 7.6 is an inversion, 7.3 is an inversion, rather, 7.6 is an inversion, 7.8 is not, 7.9 is not, but 7.2 is, and that's all of the inversions for 7. Well, of course, the thing that we really want to do is we want to be able to find the inversion number of alpha, and the inversion number of alpha is nothing more than the total number of all of these guys. And the easiest way of counting them is to realize that I've actually written them in a nice organized table that has 1, 2, 3, 4, 5 columns and 1, 2, 3, 4, 5, 6 rows, and hence the inversion number of alpha is 30. And as a consequence, we know that alpha is an even permutation, because remember, our definition of an even permutation is that the inversion number happens to be even. Now it's time to find the inversion number of first do alpha, then do gamma. And here again, I have the permutation written down for you. So please stop the video, and then when you've got all of the inversions, start the video and you'll be able to compare your answers with my answers. Well, here's the list of inversions that I found for first do alpha, then do gamma. And again, since we're looking for the inversion number, what I want to do is I want to count everything in this particular table. Well, let's first of all get inversion number of first do alpha, then do gamma. And now we'll do the quick count. We've got 1, 2, 3, 4, 5 columns still, and I've got 1, 2, 3, 4, 5, 6, 7 rows. And so the inversion number turns out to be 35. So it turns out that first do alpha, then do gamma is an odd permutation. So in other words, composing alpha with gamma changed the parity of the inversion number, and we're also going to say that that means it changed the parity of alpha, and we'll just leave it at that. All right, on this slide we have alpha up here, we have first do alpha, then do gamma here. You'll notice that the differing columns are highlighted in red. On this side, of course, we've got the inversions of alpha, and over here we've got the inversions of first do alpha, then do gamma. And the first thing that I want to do is I want to highlight the list of inversions in gray that appear in both of the lists of inversions. So 7.1 is on both of them. 7.4 is on both of them. 7.5 is on both of them. 7.3 is on both of them. 7.6 is on both of them. 7.2 is on both of them. 10.1 and 10.4. 10.5, 10.3, 10.6, 10.8, 10.9, 10.10. The 12s, 12.4, 12.4 is there. 12.5, 12, 3, 12, 6, 12, 8 is back over there, 12, 9, 12, 2, and 12, 11 are all on both lists. But this 4, 3, he's not on this list over here. So we're going to leave him unshadowed right now. This 4, 2, however, is over there. He's right there. So we're going to go back to shading. 4, 2 appears on both lists. 5, 3 appears on both lists. 5, 2 appears on both lists. 3, 2 appears on both lists. 6, 2 appears on both lists. 8, 2 appears on both lists. And 9, 2 appears on both lists. Now, what I want to notice is that we've got one inversion over here that does not appear anywhere over here. And we've got a total of 1, 2, 3, 4, 5, 6 inversions over here that do not appear over on this one. And that's actually explains why the inversion number of first do alpha, then do gamma is what it is. So let's actually kind of write that down and say what we can say. It turns out that the inversion number of first do alpha, of first do alpha, then do gamma, is going to be the inversion number of alpha minus the number of inversions in alpha that are not in first do alpha, then do gamma. And then we're going to add in the number of inversions in first do alpha, then do gamma that are not in alpha. And when we look at that, that turns out to be 30 minus 1 plus 6, and of course that is 35. But there's something else that I want to notice, and I'm going to do this when some more highlighting. I think I'll use yellow to highlight. I want to highlight these inversions that are found in only one of the two permutations. Every single one of these involves either a 4, they all involve either a 4 or an 8. And there's one, if you go looking for it, it's right here, that involves both the 4 and the 8. In other words, all of the yellow inversions, the ones that appear in only one of the two permutations, happen to be inversions that involve numbers in these two columns. In particular, they are inversions involving that 4 and that 8 and this 8 and this 4. And the other numbers that are involved in these inversions wind up being ones that are in the bottom row between those two numbers. In other words, when we start to analyze this, we realize that the inversions that involve these elements out here and these elements out here and not the elements in here are going to be on both of the lists. So when we start trying to generalize this, the important thing is that we're going to be looking at the part of the two permutations that lie between the numbers moved by gamma on the bottom row. And we'll look at that idea in the next video.